Okay, we're on chapter 13, I believe, gases. And we talked about obviously three of the main sort of gas units that's very commonly that we come across, and that is millimeters of mercury, torr, and atmosphere, and some relationships which are obviously important. Um, one torr is the same as basically 1 millimeter of mercury. It's a one-to-one relationship. One atmosphere is equal to 760 torr, and that also equals 760 millimeters of mercury. So that 760 is an important number there. It is basically your conversion factor to go between these three. And again, these are probably the three most common units you'll come across. So if you have atmospheres and you want torr or millimeters of mercury, you need to multiply by 760. And obviously, if you have torr or millimeters of mercury, you need to divide by 760. And that'll convert you into atmospheres. We started talking about some gas laws as well. We got to a few of them, I think. We got to Boyle's law, and Boyle dealt with pressure and volume relationships. So P1 V1 equals P2 V2. This is at constant temperature. Relationship that we saw there was as pressure went up, the volume went down. So the smaller volume, we're going to have more collisions. More collisions leads to more pressure, and vice versa. As the pressure goes down, that we would see a volume that goes up. We also saw, I think, Charles' law, and that is V1 over T1 equals V2 over T2. This is at constant pressure in this case. And here, like all gas laws, temperature, as we talked about, does need to be in Kelvin. So that again should be sort of an automatic for you. As soon as you're doing any type of gas law problem, you got temperature, you should always convert it to Kelvin. A reminder that even if the problem gives it to you in Celsius, they want the answer in Celsius, it does need to go into Kelvin and into the gas law, and then you have to convert it afterwards. So just keep that in mind. What we saw here was because we want to keep constant pressure as the temperature increases, the volume will also increase to adjust to allow the pressure to remain constant. As temperature goes down, the volume will also decrease to again keep the constant pressure. So we do see sort of a increase or decrease with the volume, and that's how it's able to, thank you, to basically keep the pressure constant in the situation. There's Guy Lussick's law, and that dealt with pressure and temperature. So P1 over T1 equals P2 over T2. This is actually at constant volume. So in this particular case, because it's at constant volume, we don't have the adjustment of the volume like we do in Charles' law. So what we see in this case is as the temperature increases, there's no end result that's going to happen other than the pressure is going to increase as well. Because the volume's not going to change. So we're going to have an increase in the number of collisions, and that's going to cause more pressure. And vice versa, as the temperature drops, we will see a drop in the pressure as well. We also saw, I believe, Avogadro's law. There. I remember Avogadro's law does deal with moles, and that is V1 over N1 equals V2 over N2. This is actually at two types of conditions, constant pressure and temperature. And one of the things that we talked about or sort of saw with Avogadro's relationship there is as the number of moles increases, so does the volumes. And we could kind of do some stoichiometry if it's a gas situation under constant pressure and temperature. We could kind of do a volume to volume relationship using the coefficients from the balance equation, just like we do a mole to mole relationship. And it can kind of allow you not to have to use sort of a gas law. Kind of putting all these together, I think we finished up on the big one there, which is PV equals nRT, and that's the ideal gas law. And this is different than the others, as again, it is basically just a one situation, so there's no two pressures, no two volumes, nothing like that. It also is really the most restrictive in terms of units, and clearly on all these other guys here, temperature does still need to be obviously in Kelvin. The pressure, when you're using the ideal gas law, the units has to be in atmospheres. The volume has to be in liters. N should hopefully be moles. T does need to be Kelvin. And R, PV, R is the gas constant here. And that is 0.08206 liters times atmosphere, Kelvin times mole. And that's really the reason why everybody else has to be in those units, so it all properly cancel out. A couple other things I think we touched upon as well was the idea of, I'll go up here, STP, that is standard temperature and pressure. And that is a temperature that corresponds to 273.15 Kelvin and a pressure of 1 atmosphere. And remember that if you are at STP, 1 mole of any gas will equal 22.414 liters. So again, this is a conversion factor that you could use. You do have to be, as we talked about, at STP in order to use that. And it can allow you really not to have to use the ideal gas law. But if you don't want to remember that one, you don't really have to. You could just put everything into the ideal gas law and just solve it that way as well. So it works that way. Any questions on any of that there? Okay, then I think we did. I think we did. I think we did this example to finish up on. I think so. I think we are on this one. So why don't we try this one? Calculate the pressure exerted by 32.5 grams of SF6 gas in a steel vessel with a volume of 252 milliliters and 45.5 degrees Celsius. So sulfur 3207, fluorine pretty much 19, we'll call it. All right, give it a go, see what you come up with. Okay, so let's take a look. What we want to do always is kind of pull out the information. So we are looking for a pressure. We have some grams given to us. And if we have grams, we could definitely get to moles, right? So we have N basically. We have a volume that is 252 milliliters and a temperature that is 45.5 degrees Celsius. We always have R available to us, never given to us in a problem. That should really point you in the direction of the ideal gas law, PV equals nRT. We essentially have volume, temperature, R, and we could calculate N, which means we could use that to solve for the pressure. We do have to do some conversions here, so we do need to get our grams into moles, so 32.5 grams of SF6. We'll use the molar mass from the periodic table there, and it looks like that's 3207 plus 6 times 19. Looks like it's 146.1. So that's going to give us our moles here. And it looks like we will end up with 0.2225 moles of SF6. Remember that our volume does need to be in liters, so we need to do a conversion there. So 552 milliliters, 1,000 milliliters in a liter, going to give us 0.252 liters. And like normal as well, our temperature needs to be in Kelvin, so we'll add 273.15, and that will get us there. I punched the number in right, it'll get us something maybe. About 318.65 Kelvin. And let's get any questions on that there. Now that we got everybody in the proper units, we're going to rearrange our ideal gas law. Again, not really written as a fraction, but you can think of it like that. And we're going to solve for pressure, so we need to move volume to the opposite location, which is on the bottom, basically dividing by it. And that gives us P is equal to nRT divided by V. Putting in our numbers here, 0.2225 are 0.08206. There's atmosphere Kelvin mole, and our temperature there, 318.65 Kelvin, all divided by our 0.252 liters. Liters will cancel, moles will cancel, Kelvin will cancel. That's going to leave us atmospheres as the only unit left off of the R. And that will get us here. Looks like maybe. It's like about go 23.1 atmospheres. Pretty big pressure. Any questions on that calculation there? So again, the important part with the ideal gas law is definitely you want to make sure everybody gets to the proper units. And again, if you're not sure, but you do at least remember the units associated obviously with R, that is what everybody else's units need to be in, basically. Question on the ideal gas law here. All right, the next thing we're going to talk about is changes in pressure, volume, and temperature, pretty much all the variables there. And if we actually take the ideal gas law, PV equals nRT, and because R is a constant, we could solve for R in two situations. And because these numbers are the same, they're equal to each other, we can then set the other part of it equal to each other. And we do get this relationship down here, which is P1 V1 over N1. T1 equals P2 V2 over N2 T2. In a lot of cases, the moles won't change all that much. So this one sometimes reduces down to this, which is P1 V1 over T1 equals P2 V2 over T2. This is what is sometimes referred to as the combined gas law. And our normal sort of situation here, temperature needs to be in Kelvin. Pressure here doesn't really matter as long, again, they're the same units on both sides. Same thing with the volume, as long as they're the same units on both sides, it really doesn't matter. Everything will cancel out completely. So this is one you can use when you got a change in all three of those variables or some changing happening in those three variables. It is also a really good gas law to know and memorize because frankly, you could get a lot of information from this gas law. So if we were to memorize this gas law, for example, P1, V1, and even remember it with the N in it, so N1, T1 equals P2, V2, N2, T2. And let's just say, for example, I come across a problem and it doesn't really mention anything about moles or temperature, or you're told it's held constant. If that's the situation, then essentially all you have to do is just scratch those things out that are constant, are not even mentioned. And if you do that, lo and behold, here, there is Boyle's law looking at you. If you take this sort of combined gas law, and you come across a problem where they don't mention anything about pressure and they don't mention anything about moles, you can then just scratch out pressure and moles on each side. And there is our friend Charles' law. If you take this combined gas law and you come across a problem where it doesn't mention anything about volume or moles, you can scratch those out, or you're told they're held constant. Just scratch them out. And there is Guy Lusik's law. And again, if you take this sort of combined gas law here, and you come across a problem where you're told or it doesn't mention anything about pressure or temperature, or they're held constant, you just scratch them out on both sides. And there's our friend's Avogadro's law. So pretty much from this one gas law here, which is our combined gas law, you pretty much can get every single other gas law that we talked about previously by just scratching out whatever is constant, whatever's not mentioned in the problem, and you'll probably be left with the right sort of formula. Even this one, if you want the combined gas law and you come across a problem that doesn't mention anything about moles or grams, just scratch out the moles here on both sides, and you're left with the true sort of version of the combined gas law. So if I had to invest my time, since you have to know all these formulas, I would invest my time in remembering this guy. And frankly, just scratching out whatever is constant or not given to you in the problem. And for good measure, the ideal gas law, which is really where this guy comes from, is the two that I would just remember. And you pretty much can have any gas law that you need. And just by scratching out what is not given or is held constant. Any questions on that there? Okay. So let's try one here. Consider a sample of oxygen at 27 degrees Celsius with a volume of 9.55 liters and a pressure of 2.97. We change the pressure to 8.25 and we heat it to 125. What is the new volume? So take a few moments there and see what you come up with. Temperature 27 degrees Celsius, volume 9.55 liters. We got a pressure 2.97 atmospheres. We have another pressure of 8.25 and another temperature of 125 degrees Celsius. And we are looking for a volume. So again, it should really point you in the right direction. If not, again, if you remember sort of the combined gas law that we were just talking about there. And in this case, obviously, there's no mention of grams or moles, so you can just scratch it out. And now, again, you'll be left with sort of the right formula that you need. We do need to do some cleanup here on some units. So pressures are both atmospheres, so that's good. So we need to do some temperature. So 273.15 added to each of those. And that's going to get us here, looks like 300.15 Kelvin and 398.15 Kelvin. In this case, we are actually solving for V2. And again, you can kind of just number these as ones and these guys as twos, except I wrote a two there. Let's go with a one there. There we go. And in this case, V2 is here, so we want to have V2 by itself up on top. So we need to bring the P2 down, and we need to bring the T2 up when it goes across. And that would get us P1 V1 T2 divided by T1 P2 is equal to the V2. When we rearrange it, we're going to multiply by T2 and divide by P2, basically. That will get us what we need to put in here. So our P1 is 2.97, our V1 9.55 liters, and our T2 398.15 Kelvin, divided by our T1, which is 300.15 Kelvin, and our P2, which is 8.25. In terms of units, obviously atmospheres cancel, Kelvin cancels, leaves us just liters as our units that are left. And that will get us 2.97 times 9.55 times 398.15 divided by 300.15 and divided by 8.25. It's going to give us a volume here of 4.56 liters in this case. Yeah. Any questions on that there? So again, this one sometimes gives people a really hard time sort of rearranging. Remember, just opposite locations, and whatever you want to solve for needs to be up on top by itself, basically. Yeah. Any questions on the combined gas law? Really good one. Gets you all the other gas laws pretty much. All right, so let's then talk about the same one. Let's talk about stoichiometry that involves gases. And stoichiometry that involves gases is pretty much the same type of thing that we do with all stoichiometry problems. We will still do our balance our equation. We will still do convert to moles. Remember always, if we are doing a stoichiometry problem, we also need to determine, is it a limiting reagent problem? We would then do our mole to mole relationship. And then converting our mole to some other units. So how does this different with gases? Really, the truth is somewhere along the way, you're probably going to use PV equals nRT. So somewhere along the way, you're going to kind of use the ideal gas law. You could use it up here, very front of the calculation, and if you did, you most likely would be solving for moles, and moles would equal PV over RT. Probably in a lot of cases, you'll use it down here at the very last step, and you'll solve for something maybe like volume is a very common sort of outcome of it. So either in both places you may use it, or in one place. And again, everything else is pretty much the same. You work it like a normal stoichiometry problem. It's just somewhere along the way. Usually you should use the ideal gas law, maybe in multiple places, but at least one place in that calculation. Any questions on that there? Let's take a look at one here. So there's the arrow. So for example, what is the volume of CO2 that is produced at 37 degrees Celsius and 1 atmosphere when 5.6 grams of glucose is used up in this reaction? So let's take a look. We want to figure out the volume of our CO2, which is a gas. We have some other gas type information given to us, like a pressure of 1 atmosphere. We also have a temperature of 37 degrees Celsius. Remember, we also always have R that's never given to us, but we always have it available as well. So if we think about CO2 and the PV equals nRT, I do have the pressure. I do have the temperature. R is a constant, and I'm looking for volume. So the one thing that I'm really missing in order to use the ideal gas law is moles. And the moles of the CO2 is actually going to come from the stoichiometry part. And if we take a look at sort of the other piece of information we have is we are starting with 5.6 grams of this glucose over here. So we're just going to use stoichiometry here like normal, and we're going to end up with the moles of CO2, and that's going to be really kind of the last piece that we need to kind of solve the problem. So we'll just start like normal, which is I have a balanced equation, so that's good. I'm going to take whatever they gave me and convert it to moles, which would be this guy. So we're going to do number 2, which is convert to moles, 5.6 grams, C6H12O6. I'll go to the periodic table and calculate the molar mass of this thing. That is 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens, plus 6 times 16 for our oxygens. That's going to give me 180.2 grams per mole of C6H12O6. The grams would cancel out in this case. That would actually give me moles of this guy. And if I stop there, that would not be great because I do need to get over to CO2. So this is basically our second step. I'm going to do my third step here without getting an answer at this point. You could get an answer and continue on. But to do my third step, I would go to the equation, and I can see for every 1 mole of my C6H12O6, I get 6 moles of CO2. And again, that is the mole to mole relationship between these two guys, just like we do in a normal stoichiometry problem. So here we want to get rid of the C6. So we'll go with 1 mole of C6H12O6 gives me 6 moles of CO2. Again, those guys are going to cancel. And that will get me 5.6 times 6 divided by 180.2. It's going to give me 0.1865 moles of CO2 in this case. That is sort of the last thing, as I mentioned earlier, that's missing from our ideal gas law to allow us to solve this problem. So now we can use our ideal gas law in the last step of our stoichiometry problem here. We're going to use PV equals nRT. We're going to be looking for a volume, and we now have everything we need for CO2, basically. We do have to, because it is the ideal gas law, make sure everybody's in the right units. So obviously here we do need to change our temperature to Kelvin. So we'll take our 37 plus 273.15, giving us 310.15 Kelvin. Atmospheres is good. Gas constant is good. So solving this for volume will be nRT over P. Gives us the N, which is 0.1865. Our R is 0.082. Oops, 8. And come here. Try that again. All right, 0.08206 liters atmosphere Kelvin mole. Our temperature being, in this case, 310.15 Kelvin, all divided by our pressure, which was 1 atmosphere. So atmospheres cancel, moles cancel, Kelvin cancel. Going to leave us liters here as the only unit left. Liters. And if we do that, we will end up with and we'll end up with 4.74, we'll call it liters in this case. And that would be 4.74 liters of CO2. By the way, that would also be considered a theoretical yield in volume, and that would be our theoretical yield in this case. Any questions on that there? So hopefully you can see it is really the same sort of stoichiometry steps. Again, in this case, and very commonly, kind of using the ideal gas law in the very last step. Can use it the second step as well, sometimes as well. Any questions on that one there? All right, so why don't you try one then? Let's try this one here. What volume of hydrogen gas at 27 degrees Celsius and 1.25 atmospheres is required to react with 5.65 grams of phosphorus there? Interested in the hydrogen over here, which is a gas. So in terms of the hydrogen, we want to know what is its volume. We have some other gas sort of information, like 27 degrees Celsius for our temperature. We have a pressure that is 1.25 atmospheres. And again, we always have sort of R available to us. So again, if we just kind of look at the ideal gas law, which is probably what we're going to use, we're looking for our volume again. We again have temperature, R, and P. So once again here, we are missing, to kind of solve for it, the moles of the hydrogen gas. That's going to come from the stoichiometry and the other piece of information, which is we are starting with 5.6 grams of phosphorus. So we're going to use a mole to mole relationship between these two so that we can again get our moles of hydrogen that we need for our ideal gas law. So to do that, we're going to balance the equation, which it is, hopefully 12, 12, yep. And second, we're going to take what they gave us and convert it into moles. And so 5.65 grams of P4. We'll use the periodic table there and get the molar mass of P4. That's going to be 4 times 3097. That'll give us 123.9 grams per mole of P4. That is going to convert us into moles of P4. That'll get us 5.65 divided by 123.9. Going to give us 0.0456 moles of P4. Remember, though, that we're not really interested in moles of P4. We're just using that to get ourselves over to hydrogen, which is what we need. And from the equation, we can see for every 1 mole of P4, we get 6 moles of H2 out. So that's going to be really our third sort of stoichiometry step, converting our P4 into H2 using the equation. So 1 mole of P4 gives me 6 moles of H2. Those are going to cancel. So basically here we're going to multiply that by 6, it looks like. And that'll get us 0.2736 moles of H2, which is, again, the last missing piece that we need to use the ideal gas law. Any questions on that so far? All right, now that we have it, we really do step number 4. Once again, with the ideal gas law, and we got everything here, we're going to solve for volume. Volume will be nRT divided by P in this case. Looks like here the only thing we got to convert out is our temperature, so 273.15. It's going to get us there 300, I think, 0.15. Everybody else should be okay, so we'll take the moles we just calculated. We'll use our ideal gas law here. And we'll use our temperature, 300.15 Kelvin, divided by our pressure of 1.25 atmospheres. The moles here will cancel, the Kelvin will cancel, the atmospheres will cancel. It's going to leave us liters left over, which is good since we are looking for a volume. And that volume is going to be 0.08206 times 300.15 divided by 1.25. Looks like we're going to end up with about 5.39 liters of H2. This again would not be a yield because this is a reactant. So that'll just be how much volume of H2 you need to throw in there. So again, really the same 4 steps as a normal stoichiometry problem. Just got to kind of incorporate that ideal gas law into it. Any questions on that there? Let's take a look then at one more here. I think, there we go. This is actually the experiment we're going to be doing today. So see what happens here. Magnesium reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. We want to calculate the volume of hydrogen gas produced at STP if you started with 5 grams of magnesium. So why don't you give it a go, see what you come up with. Good practice for today. Okay, so let's take a look. So this is pretty much the lab today. You're gonna take some magnesium, react it with some hydrochloric acid, and you're gonna produce some hydrogen gas. And we're interested in this case, and like in lab, how much hydrogen gas we're going to be produced. So we're interested in the volume here of hydrogen gas. It is at STP is what we're interested in. Remember, STP is standard temperature and pressure. And those actually are values. So the temperature is 273.15 and the pressure is 1 atmosphere. So again, that is basically the meaning of STP. We also always, again, have R available to us if we need to use it. So again, if we want to look at the PV equals nRT, we see a similar sort of outcome as we've been seeing. We have temperature, we have R, we have pressure. We're looking for volume. Once again, here we are missing the moles of H2. That will be supplied to us through stoichiometry because the other piece of information we have is that we are starting with 5 grams of magnesium. So once again, here we're going to use stoichiometry to get us moles of hydrogen that would be produced, and we could then use it in our gas law. So we'll start like normal. We got a balanced equation. We're going to convert to moles. So we're going to take our 5 grams of magnesium. Use the molar mass there. Magnesium, 2431 grams per mole. That's going to give us moles of magnesium. If you want to get an answer, you can. You don't necessarily have to, but you could. And if you do, maybe not round too much here. 8 moles of magnesium. Again, here we're not interested in magnesium. We're interested in hydrogen. So we're going to use our mole to mole relationship between those. And from the equation, it's a pretty straightforward one. 1 mole magnesium gives us 1 mole of hydrogen. So it is a 1-to-1 relationship, which is not bad. It's a 1 mole of hydrogen gets us 1 mole of magnesium here. That'll be like our third step. And we'll end up with 0.20568 moles of hydrogen. That again is the missing piece that we need here to use our ideal gas law. So now that we have that, we can kind of use it. PV equals nRT. Again, in this case, we're going to solve for volume. So volume would be nRT divided by P. In this case, everybody's in the right unit, so we don't have to worry too much about that. So 0.20568 moles are 0.08206 liters atmosphere Kelvin mole. Our temperature at STP 273.15 Kelvin, and our pressure 1 atmosphere here. Atmosphere is going to cancel, Kelvin going to cancel, mole's going to cancel, going to leave us liters as our answer. And I think we'll end up with here. About 4.61 liters of H2. This would be a theoretical yield as our hydrogen is a product, so that would be the theoretical yield. That's how much volume of hydrogen gas you should collect in this reaction if you started with 5 grams of magnesium. And again, pretty much the same 4 steps of stoichiometry, just using our ideal gas law here at the end. Any questions on that one there? Now, we could have, if we wanted to, and we recognized we were at STP conditions in this particular problem, which means because we were at STP conditions, we could have used, if we wanted to, that relationship that we saw earlier, that 1 mole of any gas equals 22.414 liters. And by doing so, we could have just picked up right here, and instead of using the ideal gas law, we could have just took our moles of hydrogen that we calculated and used that relationship because we were at STP, 22.414 liters is 1 mole, and that will get you there as well. So this is an alternative way you could use it. Because again, we could do that because we were at STP conditions. Again, if you are not at STP conditions, you cannot use that. But in this case, you could have used it. So you did have a couple different ways you could have got there and kind of the fourth step, you could have used the ideal gas law, which always works in any situation, STP or non-STP conditions, or if you wanted to, you could use that conversion because we were at STP conditions. Any questions on gas stoichiometry here? Pretty identical calculation to what you will do in lab today, pretty much. Yeah. Any questions on that there? Yeah. We will not be at STP conditions, but you will be asked to convert it to STP conditions and calculate what your volume would be at STP conditions. Yeah. So we won't be doing the experiment at STP conditions, but you're going to turn your result into what it should be at STP conditions. Other questions? All right. I think we'll lay it up there for today, and obviously we're going to go do this.